Hey guys, it's Bruno, the IB Math teacher. Welcome to week number 7 now of the Ace Your IB Math Exams in 10 Weeks challenge. If you don't know me, I'm Bruno. I used to work at one of the most prestigious IB schools in Brazil as the head of departments, as an HL math teacher, and also I'm an IB math examiner. And for this May 2026 cohort, I've decided to launch this 10-week challenge or 10-week course to better prepare you for the upcoming IB Math, the May exams in IB Math. Each week, we tackle all 5 topics in IB Math, so functions, number and algebra, trig, statistics, and calculus. 1 question per topic. None of the questions is easy. They're all demanding. We mix paper 1 and paper 2 style questions. All of them are IB Math style questions. And this is a way to mimic what you're going to face when you enter your examination room. So you're not going to know exactly what's going to show up in the IB Math exam. So we're tackling all sorts of questions. Do find the PDF in the description of this video so you can download it, print it, and work it out as we go along the video, as we go through the video. And do share these resources with your colleagues as well so you guys can practice together. So let's get to it. Let's get to week number 7 of the Ace Your IB Math exams in 10 weeks. So let's start with exercise number 1, one that involves a binomial expansion with an exponent which is unknown. And the most difficult types of binomial expansions, they usually involve that, a unknown exponent. Now, what do we have here? We need to find that specific exponent given that in the expansion of root 2 plus 2 over x to the n, the coefficient of the term in x to the negative 5 is 4 times the coefficient of the term in x to the negative 1, meaning when you do the expansion, you're going to have something x to the negative 1 and also something else x to the negative 5, and this coefficient here is 4 times this coefficient here. Now, how do binomial expansions work? When you expand a plus b to the n, what you get is n choose 0, a to the n minus 0, b to the 0 plus n choose 1, a to the n minus 1, b to the first power, all the way up to n choose n minus 1, a to the first power, b to the n minus 1, plus n choose n, b to the n power times a to the 0, which is just 1. And do notice that over here, a and b are root of 2 and positive 2 over x, which means that when we're expanding that, what we get is n choose 0 root 2 to the power of n 2 over x to the 0 plus n choose 1 all the way up to the last 2 terms, which are n choose n minus 1 root 2 to the first power 2 over x to the n minus 1 plus n choose n root 2 to the 0, which is 1 times 2 over x to the n power. Now we can erase this now. And by the way, if you're wondering, you do have that formula in your formula booklet. Here it is. So you don't need to memorize it. Now continuing. We are looking for the term in x to the negative 5 and also the term in x to the negative 1. That being the case, we need to ask ourselves which one of these will produce an x to the negative 1. And it could be somewhere in the middle here as well. Now, given that a binomial coefficient is just an integer, given that root of 2 to the power of n is a number, could be an integer, could be an irrational number depending on the power. From these 3, the only one which is going to influence and create a power of x is this last one, meaning that we need to focus on them. And we can already spot the first one, the one which produces a term in x to the negative 1, which is this. Notice over here that we have 2 to the first power over x to the first power, which is of course 2 times x to the negative 1. So I'm going to color code this purple. And also notice that none of these will produce x to the negative 5. We actually have it showing up somewhere down the line here. Specifically when we have a 2 over x to the 5th power, which means that we're going to have n choose 5 as well, given that it's this 5 that shows up in the exponents of b, and also times root of 2 to the n minus 5. And this continues. So color coding again, this is the term in x to the negative 5. You might be wondering, can I use the formula for the kth or the k plus 1th term of an expansion? And yes, you can. I just didn't use it because I wanted to go through this explanation, and also that's not a formula that you find in the formula booklet, which doesn't mean that you cannot apply it in your IB exam. If you were to use it, which by the way is this one, you would still need to ask yourself what k value will produce an x to the negative 1, which means 1 over here. So you would still find the same thing. And also ask yourself which k over here would produce an x to the negative 5, which means a 5 over here, which will produce a 2 to the 5th over x to the 5th, which is 32 x to the negative 5. So again, we would get to the same place. Now continuing with the exercise. In order to find n, we need to work with what was given by the exercise, this extra piece of information. The coefficient of the term in x to the negative 5 is 4 times the coefficient of the term in x to the negative 1, meaning the red and the purple ones. And what are the coefficients? They are the numbers that multiply the variables, which means x to the negative 1 and x to the negative 5, so the variable x, which in this case means n choose 1 root 2 to the n minus 1 times 2 to the first power, and in this case n choose 5 root 2 to the n minus 5 2 to the 5th. Do notice that we're not taking into account x's. So we know that n choose 5 root 2 to the n minus 5 times 2 to the 5th power is equal to 4 times the coefficient of the term in x to the negative 1, which means n choose 1 root 2 to the n minus 1 times 2 to the first power. Now this is when we realize why this is a paper 2 question. GDC is allowed, and by the way, I never mentioned it, but this is a paper 2 style question. But before we start plugging things into our GDCs, let's just simplify this as much as possible. So what is n choose 5, for example? Given that a choose b is equal to a factorial over b factorial times a minus b factorial, we have as n choose 5 n factorial over 5 factorial, which is 120, times n minus 5 factorial. This times root 2 to the n minus 5 times 32 is equal to 8 n choose 1, which is n, and you can use this formula to verify, times the root of 2 to the n minus 1. Now we can simplify this 8 with this 32, that gives us 4 and 1, and this 4 with a 120, which gives us 1 and 30. So we have n factorial over 30 n minus 5 factorial times root of 2 to the n minus 5 equal to n times root 2 to the n minus 1. Now given that n factorial can be written as n minus 1, n minus 2, n minus 3, n minus 4, n minus 5 factorial, we can also simplify the n minus 5 factorials, and we can also cross multiply this 30, which gives us the following expression, or actually equation. Now what can we do from this point on? We can certainly simplify these n's, and also we can divide both sides of this equation by root 2 to the n minus 5. That allows us to get rid of this, and given that we have the same base here, we can write root 2 to the n minus 1 over root 2 to the n minus 5 as root 2 to the n minus 1 minus n minus 5, meaning root 2 to the 4th power, which is equal to 4. So we have n minus 1, n minus 2, n minus 3, n minus 4 equal to 30 times 4, so 120. And this is when you plug this equation into your GDC, after you simplify it a lot. And when you do it, when you use the numeric solver, you get n equals 6. And do let the examiner know that you used your GDC in this step. And then we're done. All right, so in this question number 2, you're going to need to be super comfortable with not only finding equations of lines, but also how to deal with composite and inverse functions. Now, what we have here is a function that consists of 2 line segments connecting these 3 points. So 0, 10, 4, 0, and then 4, 0 to 12, 4. If we're trying to evaluate f of 2, the first thing that we need to find is f of 2. And remember that f of x is a piecewise function, therefore all of this belongs to f of x. Therefore f of 2, we can see from the graph that it's equal to 5. If the graph crosses the grid at that particular point, then you're fine. You can, by inspection, grab that value or use that value. However, when it doesn't, you cannot make any assumption. And that's exactly what's going to happen in the second step of this exercise. So we do have f of 2, which is equal to 5. Therefore, we need to find f of 5. In this case, it's pretty clear that f of 5 will be 1 over 2. However, as I mentioned, and let this serve as an example for other IB math exercises, let's not make any assumption. Let's actually find the equation of this line segment. So we can then replace 5 in x. Of course, we're gonna get half as a result, but let's get there analytically by taking delta y and dividing by delta x, which means 4 divided by 8. And if the slope is 1 over 2, we can finish this by finding b, replacing one point that the line crosses. So that could be 4, 0 or 12, 4. And let me replace 4, 0 just because it's easier. Now we get b equal to -2. Therefore, the equation of this line segment is 1 over 2x minus 2. And this is, of course, valid from 4 to 12. Now we can find f of 5 by replacing 5 into the x value, which gives us -half. So f of 2 is -1 over 2. Now we have another function now that we need to consider. G of x is equal to 2x plus 1 over x minus 1. And if we're trying to find the solutions for the equation g of f of x equal to 3, remember that the last thing that is done in this process is to evaluate g of something. And in this something, of course, is f of x at some particular point. But we know the result for it. The result is 3. Therefore, we need to have something here, which when you input into g, produces 3 as a result. Now, producing 3 as a result in g of x means that you're not plugging in 3 into the x values or into x over here and over here. What it actually means is that the result is 3. Therefore, this g of x is going to be 3. We need to find the x value that produces 3 as a result. And that means that we need to find where 3 is equal to 2x plus 1 over x minus 1. After cross multiplying, we get 3x minus 3 equal to 2x plus 1. Therefore, x is equal to 4. So whatever shows up inside over here, well, that has to be equal to 4. Therefore, this question mark, we know it is equal to 4. And now we have a different question to address, which is, where is f of x equal to 4? Now, again, we're not placing 4 into x, but we're actually reading what the input should be in order to get 4 as a result. And f of x is equal to 4 over here and over here. Now, we can clearly see that when x is equal to 12, we do get 4 as a result. That's the edge of this line segment. However, we cannot see precisely what the second value is, which is this one. So let's call these points A and point B. We do have point B, so now we need to find point A. So f of x is going to be equal to 4 at x equals, or when x is equal to 12, and when x is equal to something. We're going to find that something right now. Using a similar process, we're going to find delta y and delta x. In this case, the line is decreasing, therefore the slope will be negative. We have -10 over 4, which is the same as -5 over 2. So y is equal to -5 over 2x plus some constant b. Let me just call this c because we used b before. And now we plug in any points that this line segment crosses, for example, 0, 10 or 4, 0, which are the edges actually. So we can find c. So let me use the points 0, 10. So 10 equals -5 over 2 times 0 plus c. c, which is the y-intercept, is equal to 10. So everything makes sense. It should be 10 because that is the y-intercept. So the equation of this line segment is -5x over 2 plus 10. And this is valid, of course, from 0 to 4. Now, when is this equal to 4? Well, 4 equals -5 over 2 times the x value, which is this value right here, which we're going to find, plus 10. So -6 equals -5 over 2x. Therefore, that second x value is 12 over 5. You see, this looked like a harmless exercise, but it turned out to be trickier than expected. The coordinates of this point are 12 over 5 comma 4. So we have two different solutions. Now, if you want to check if this actually makes sense, if this actually produces 3, you can always double check, of course. So for example, let's take these two scenarios into account when x is equal to 12 and when x is equal to 12 over 5. So for x equal to 12, we have g of f of 12. We know that f of 12 is 4, so we have g of 4. And g of 4 is 2 times 4 plus 1 over 4 minus 1, which is equal to 3. So it works. Now, using the second case, we have g of f of 12 over 5, which is g of 4, given that this is the point 12 over 5 comma 4. And we know that g of 4 is equal to 3 because we just found that. So that's pretty much it. In this question number 3, we have a trig question, of course, topic 3, trig, that involves area of triangles, it involves the cosine rule, and a trig identity. So lots of concepts inserted into the same question. So let's tackle it. We know for a fact that the area of this triangle is 42. We have sides x plus 2, which is the shortest one, and the other ones are 2x and 3x minus 1. Now, using the formula for the area of the triangle, we're going to write down an expression for sine of theta in terms of x. And in the area, or in the formula of the area of a triangle, we do have sine of something. In this case, it's going to be sine of theta there. So let's apply it. When you're using the formula for the area of a triangle, do know, of course, that between A and B rests angle C. Angle C is there. It's the angle in between these other two sides. So we're not going to use, in this case right now, x plus 2 in this formula. So the area is 1 over 2, 3x minus 1 times 2x times sine of theta, which is equal to 42. We know that the area is 42. We can simplify 2.5. And given that on the left-hand side, we have x times 3x minus 1 times sine theta, and on the right-hand side, we have 42. Therefore, we can write sine of theta as 42 over x 3x minus 1. Now, we're going to apply the cosine rule to write down and simplify an expression for cosine of theta now in terms of x. When we're applying the cosine rule, this side and this angle, they're opposite to each other, which means that we're going to use these as the side that shows up on the left-hand side, and this is the angle that shows up on the right-hand side of this formula. So we have x plus 2 squared equal to 3x minus 1 squared plus 2x squared minus 2ab cosine of c, or cosine of theta in this case. So we have x squared plus 4x plus 4 equal to 9x squared plus negative 6x plus 1 plus 4x squared. And by writing 3x minus 1 times 2x as 6x squared minus 2x, we get negative 2, 6x squared minus 2x. All of this times cosine of theta. Now we can simplify these terms, writing them as negative 12x squared on the left-hand side of this equation. Also the x's, so plus 10x, and simplify the 1 with the 4. So plus 3 equal to negative 2, 6x squared minus 2x cosine of theta. Now cosine of theta can be written therefore as negative 12x squared plus 10x plus 3 over negative 2, 6x squared minus 2x. So there you go. This is an expression of cosine of theta as a function of x. Now in exercise number 3, we're going to gather all this information, sine of theta and cosine of theta, and by using the trig identity sine squared plus cosine squared equals 1, we're going to find the value of x. Now do remember that this is a paper 2 question, so you can use your calculator, and there will be no other way actually. And you can solve it. You can find your x value using one of these two possibilities. You can either graph it, or graph the equation, or the left and the right hand sides, or use the numeric solver in your calculator to find the x value. So either one of those is fine. So what do we have in question C? Sine squared plus cosine squared is equal to 1. Therefore, we're going to square this guy, and we're going to square this one as well and place it over here. Now using the numeric solver, and careful when you're inputting this equation into your GDC, because it's very easy to make a typo. And by the way, you can always move this 1 to be on the left hand side, so you have 0 on the right hand side. So you get this. So let's type it in. And by selecting an appropriate interval, guessing for example at 10, we get approximately 5.86. And with this in hand, we can find what cosine of theta is by plugging 5.86 over here, over here, over here, and over here. And we get a cosine of theta equal to 0.9018 ... which means that theta, which is the arc cos of that, is approximately 25.6 degrees. All right, so let's jump to this statistics problem, which is by all means not the most sophisticated one, but it's a kind of exercise that shows up every time. And by every time, of course, I don't mean every year, but occasionally it does show up. Now, we have a tire manufacturing company that is, in a nutshell, testing whether the tires maintain or hold the air pressure. So they take a tire and just leave it there for a few days and see how the tire pressure reduces with respect to time. Now, over here we have time measured in days, and x is used to specify the number of days. And we have tire pressure being modeled by the variable y. So y as a function of x measures the tire pressure as a function of the days that it is stored in this climate-controlled environment. Now, in order to write the regression line of y with respect to x, we need to use our GDCs, which means that we're going to do a linear regression. So the first thing to do is to populate our table with these values. So we're going to edit our table, and I'm going to use L1, which is the first column, to input the number of days. There you go. And then L2 to input the tire pressure. You should do a linear regression where the X list is L1. In this case, right now I'm using a TI-84. L2 is the pressure, and we're going to store, which means clicking on vars function y1, whatever equation that we get, which means a linear one, into our y1. And what we get here is y as a function of x as negative 0.445x plus 38.7 rounded to 3 significant figures. And we can see how strong the association is by checking the value of r. R is negative 0.998, which is a very strong negative linear correlation. Now, what does the gradient and the y-intercept, what do they mean? We have each data point, which is represented over here by these little dots. And this is, by the way, just a rough sketch. And we have our linear regression. Now, the y-intercept means the initial tire pressure, which is y of 0, which in our case, for this linear regression, it is approximately 38.7. This is an approximation of the tire pressure for the instant, or on the instant it was inflated. The tire was inflated. Now the gradient, which is the slope y over x, it is the rate of decrease of the tire pressure per day. Remember that you can find a gradient by doing delta y over delta x, which means the change in y over the change in x. So when the change in x is 1, which means 1 day, what we get for the slope is the change in y, which means the change in the tire pressure. Now this is negative because, well, the slope is negative in this case. It could be a rate of increase for other contexts. We can, with our model, for example, for question D, estimate the tire pressure after 20 days, which in this case is going to be approximately 29.8 psi. And we can do these calculations whenever we're inside the domain that we used to create this model. So for example, in this case, we're going from day 0 to day 24. So anything that we calculate within this range of values, it's fine. If you want to find, for example, the air pressure after 13 days, that will be fine as well. However, anything greater than 24 or less than 0, in this case, of course, less than 0, doesn't make a lot of sense. But after 24 days, the model is not appropriate. Over here, we have an extrapolation. Therefore, it is not. Something that's not appropriate as well is to find the number of days given a pressure. This model is only suited to find the pressure, the air pressure, as a function of days. If you were to find the number of days as a function of pressure, you would need to build a different model using the same data, but when you're doing the linear regression in your calculator, you need to switch the columns. So you need to use x for y and y for x. If you do that, then it's fine. In this case, it is not fine. All right, so let's get to exercise number 5, the last one in this list. And may I say, this exercise sounds or seems or looks completely harmless, but that might not be the case. Let's take a look at it. Consider the differential equation dy dx equals 2x minus 2 plus y over x minus 1, where dy dx is equal to 1 when x is equal to 0. So these are conditions given by the exercise, and we have a differential equation which you might identify as either separable, homogeneous, or one that you can solve using the integrating factor. We're going to define which one it is in a minute. But let's first find the first 3 non-zero terms in the Maclaurin series polynomial, or the Maclaurin polynomial expansion of y of x. So we're going to leave solving the differential equation for question B. Now, question A, as I said, does not involve solving the differential equation, but it does require us to remember how to perform a Maclaurin series expansion. And of course, we have the formula in the formula booklet. I'm going to place it here right now. So basically, we can approximate a function through a Maclaurin series doing f of 0, or calculating f of 0 plus x times f prime of 0 over 1 factorial, which is not mentioned here because, well, 1 factorial is just 1, plus x squared f prime prime of 0, the second derivative of f at 0 over 2 factorial, plus x cubed f prime 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 of 0 over 3 factorial, and so on and so forth. And here lies part of the problem, because we are able to find, for example, through this differential equation, f prime of 0, given that f prime of 0 is nothing but dy dx when x is equal to 0, and this is a condition that was already given by the exercise. This is just one. However, we need to calculate the second order derivative and also find f of 0. If you were to write the Maclaurin series expansion using dy dx, and I think I'm going to do that right now to make it closer to the description of the exercise, it's going to look like this. All right, so y of x is equal to y of 0 plus x times dy dx when x is equal to 0, plus x squared over 2 factorial d2y dx2, also when x is equal to 0, and so on and so forth. So again, the only thing that we have right now is this term right here. dy dx is equal to 1 when x is equal to 0. Therefore, this is equal to 1. Now, what is y of 0? This is usually a condition that's given in the exercise. They usually give us the point, and it seems like this exercise is missing that piece of information. But the thing is, when x is equal to 0, which means that this is 0 and this is 0, we know that dy dx is equal to 1. Therefore, we can find the y value at that point, or the y coordinates when x is equal to 0, using this equation right here. So we know that 1 is equal to 2 times 0 minus 2 plus y over 0 minus 1, which gives us 3 equals y over negative 1. Therefore, y is equal to negative 3. So remember, this is y of 0. Now, lastly, we need d2y dx squared, which is the second order derivative of y with respect to x, and more precisely, exactly at x equals 0. So let's first find the second order derivative of y. If we know that dy dx is equal to 2x minus 2 plus y over x minus 1, then we need to differentiate it again with respect to x to find the second order derivative. Now, finding the derivative of the first two terms is quite easy. For this one, it's just 2. For this one, it is 0. However, for the last one, we need to use the quotient rule, which will give us the following. Derivative of the top function times the function on the bottom minus the top one times the derivative of the function in the bottom over the denominator squared. Therefore, when x is equal to 0, which means y is equal to negative 3, d2y dx squared will be equal to 1, because dy dx when x is equal to 0 is equal to 1. X is just 0. We have y equal to negative 3, and over here we have 0 as well. So we get 2 plus negative 1 plus 3 over 1, also known as 4. So this guy right here is equal to 4. And the Maclaurin series expansion is then negative 3 plus x squared over 2 factorial times 4 plus dot 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 the other coefficients, the other terms. We can simplify the 4 with the 2, which gives us, as the first three non-zero terms, negative 3 plus x plus 2x squared. Now for question B, we're going to solve the differential equation algebraically. If you thought about this as not a homogeneous one and not as a separable one, but as one that has an integrating factor that we calculate using the integrating factor, which means a linear one, then you are correct. Let's do that. The overall form of a linear differential equation is the following: dy dx plus p of x y equals q of x. And we can already see that this differential equation is not in that format. It's not in that form. So let's make it so. We have dy dx minus 1 over x minus 1 y equals 2x minus 2. Now, what we're going to select as our p of x, or what is p of x? Well, that's exactly negative 1 over x minus 1, which means that the integrating factor is e to the power of the integral of negative 1 over x minus 1 dx, which is the integral of p of x dx. Now, we can move the negative outside, and the integral itself is nothing but a ln of x minus 1. And then if you're thinking about rewriting this as negative x minus 1, well, think twice, careful, this is not the case. Using log properties, we're going to move this negative to the exponent of the x minus 1. Therefore, we have e to the ln of x minus 1 to the negative 1. Therefore, our integrating factor is x minus 1 to the negative 1, also known as 1 over x minus 1. Now we're going to take this integrating factor and multiply both sides of this differential equation by it. And this is going to give us, I'm just going to copy the left-hand side right here. This is all equal to 2. Why 2? Well, over here we have a quotient of 2x minus 2 over x minus 1. You can factor out a 2 from the numerator and cancel these guys out. So we have a 2 over here. And what's the next step? The next step is to integrate both sides. Do know that if you did all the processes, if you went through all the process correctly, the left-hand side, or the integral of the left-hand side, will always and forever be y times the integrating factor. In this case, y times 1 over x minus 1. Oh, why is that the case? There's a proof, and you can find the proof in this channel. There's a video for that. But do know that the integrating factor method always produces, if you did everything correctly, of course, always produces on the left-hand side y times the integrating factor. So the only difficulty is to actually integrate the right-hand side, which is, in this case, it's not that difficult because, well, this is just a power rule, right? The integral is just going to be 2x plus c. So this is equal to 2x plus c, as mentioned before. Now, if we cross multiply, we get x minus 1 times 2x plus c. And we know from the description of the exercise, or from the exercise, that when x is equal to 0, y is equal to 3, which allows us to find the constant right here. We're going to do just that. Negative 3 equals 0 minus 1, 2 times 0 plus c. Therefore, c is equal to 3. So our y can be rewritten as x minus 1, 2x plus 3. And if you FOIL, we get the same answer as question A, as we should. And there you go, 2x squared plus x minus 3. Now, let's move to question C, which is one that involves binomial expansions with rational exponents. Let's get to it. All right, so in question C, we need to write the function 1 over 2x squared plus x minus 3, which, by the way, is the same one that we got before, as a binomial expansion up to determine x squared. So we got this before. We know even what's the factored version of this. But even if we didn't, of course, we can factor it. Now, knowing that f of x is 1 over x minus 1 times 2x plus 3, we can rewrite this as x minus 1 to the negative 1, 2x plus 3 to the negative 1 as well. We're going to expand these separately, starting from x minus 1 to the negative 1. Whenever you're doing a binomial expansion with rational exponents, it is important that the constant is 1. The binomial expansion with rational coefficients has a friendly formula if and only if that constant is 1. There are videos in this channel that explain why that's the case, so let's just focus on that. So let's start from there so we can successfully carry out these binomial expansions. And how do we transform this into a constant that's actually 1? Well, in this case, we can rewrite this x minus 1 as negative 1 times negative x plus 1. And do remember that this is all raised to the negative 1, which means that we have negative 1 to the negative 1, and we also have negative x plus 1 to the negative 1. We know that negative 1 to the negative 1, which is 1 over negative 1, well, that's just negative 1. So we have minus negative x plus 1 to the negative 1. We're going to expand then this guy right here, which is negative 1 choose 0, negative x to the 0, plus negative 1 choose 1, negative x to the first power, plus negative 1 choose 2, negative x to the second power. And knowing that negative 1 choose 0 is 1, negative 1 choose 1 is negative 1, and negative 1 choose 2 is also 1, again, there are more videos in this channel explaining this process of finding binomial coefficients with rational exponents or negative exponents. In this case, negative 1 choose 0, negative 1 choose 1. We're just going to carry on not to make this video too extensive, okay, so not too long. We have finally negative 1 minus x squared, and we only went to up to the term in x squared because that's what we're looking for. Now let's do the same thing with 2x plus 3 to the negative 1. Again, we need to make sure that this 3 is not actually a 3, it's a 1, so we're going to factor out a 3. So we have 3 times 2x over 3 plus 1, everything to the power of negative 1, which means that we have 3 to the negative 1, 2x over 3 plus 1, also to the negative 1. Therefore, 1 over 3, and then we're going to expand this binomial right here, 2x over 3 plus 1 to the power of negative 1. And this gives us negative 1 choose 0, 2x over 3 to the 0 plus negative 1 choose 1, 2x over 3 to the first power plus negative 1 choose 2, 2x over 3 to the second power. And don't forget to multiply everything by 1/3. We get 1 over 3 minus 2x over 9 plus 4x squared over 27. So ultimately, this product, x minus 1 to the negative 1 times 2x plus 3 to the negative 1 will give us, and we can grab the individual answers, negative 1 over 3, 2x over 9 minus 1/3 of x, which is negative x over 9, and then 4x squared over 27 minus 1/3 of x squared plus 2x squared over 9, which is negative 7x squared over 27, and that's it. Kind of a long exercise. All right, so that's it for week number 7. We're done with it. We just have 3 more weeks to go. Congrats, by the way, you're almost there. Do share these resources with your colleagues so you guys can study together. And do know, as you know already, everything can be found in the description of this video. Everything is for free. You can just click the links and download the PDFs there and access also the YouTube videos there. Okay, I'll see you on the next one. I'll see you in week number 8.